Так, всем привет.
Good day, I'm Daniel Sigalov, and the topic of my presentation is analysis of the client JavaScript code for detecting HTTP endpoints. I work at Moscow State University, and I also play for Bushmakers, and you also have my contact details on this slide. So I'm going to tell you about this analysis of the client JavaScript code, and we do a black box web scanner to identify vulnerabilities, and this is also the topic of my thesis. And what I'm going to tell you is not just me. It's me and a group of really cool researchers, and I had this group. So, what is the task that we're resolving? We would like to find vulnerabilities in web applications. We know how to send attack vectors, but where to put the inverted commas. You can see the vectors in red arrows, but we need to know more. We need to know the URL and other parameters, and we want to do it in automated mode. We want the scanner to work in automated mode without the toil, and it also is very helpful for manual pen testing if the scope is too large or we don't have enough time. So we're going to mine this information from web pages. So here we are. We have a web page, and we need to understand what server endpoints it addresses. With HTML, it's easy. We can look at tag, like all the tags that would allow us to get the information. How about the ones that the requests that are sent from JavaScript? Like that? Well, not like that. It's not as simple as that, because we would have to analyze code, and it's either unresolvable, algorithmically speaking, or in specific cases, it's in the very least very, very challenging. And yet we're going to try and do it. So what are the requests sent by JavaScript code onto the web page? We have endpoints and we have requests. And endpoint is in the name of my presentation. API endpoints, logic actions, they exist in multiple names, but when we say endpoints, they are sent to various parts of server code. When we send endpoints, they trigger various parts of servers, and there can be multiple requests to one endpoint, like here. So in this particular case, we're going to assume that we just want to find all the requests to server endpoints. A separate task is to understand which endpoints it was addressed. In particular, we're not going to do it for now. So, how this is being solved? The scanners today use dynamic crawling. What is dynamic crawling? A headless browser opens the page, and then some manipulations are made. Or in simplest instance, we open the web browser and we'll look at the requests that were sent from it, and then we'll look at the tree and we find the information on the new pages, in the elements, like in the links and stuff. And this is what Anatoly Ivanov was referring to in his presentation in last PhD days. It's rather easy. You can just take a library and write some bits of code, and you can easily trigger some of the requests with this kind of dynamic crawling. But how to do it with full coverage? This is an issue. Because some requests is not single step, but it's multiple step. When you have to open a sidebar menu, and then from there another menu, and then another menu, and then the request is sent. So how would you cover all of that? With the dynamic crawling, it's obviously impossible. People are working on that, but it's still an unresolved issue. Even if dynamic crawling of that exists, it would take a lot of time. We're going to look through all the menus, and we'll scroll through all the bars, etc. And some of them would not detect the requests that are there in JavaScript, but they cannot be easily identified with the was the thing that I just described. And crawling is usually done in the easiest way. You don't really press any buttons, you don't really scroll or target your mouse at anything. So our idea is this. This is a JavaScript code part on a web page. And we don't know how this function is invoked. It may be invoked after a long chain of actions or not, but we can see it's sending a request. We can understand it with our own eyes, right? So probably if we can see it with our naked eye, it could be automated. It could be difficult to trigger with request, but and sometimes a lot of codes are bundled together. So probably the client's JavaScript code could be seen, could be visible. And these requests that are not related to the web page, they would be there in the code, but it would be impossible to invoke it from the code. So it would be de facto dead. It's dead code. You cannot invoke it. So for other security tasks, when we analyze, when we are looking for DOM XSS, we cannot trigger it because it's a dead code. You cannot trigger it at all. If we're looking for information on in a different way, then that code is of interest to us. So, okay, we are going to analyze code. What are the analyzers that already exist, and can we use it? None of the analyzers, as it turned out, comes out of the box and resolves our issue, mining server endpoints from the client JavaScript code. We also realized that the static analyzers would go down or load slowly. Yes, they're all validated and correct and all, but it's too difficult for them to analyze contemporary JavaScript, and this is an unresolved issue, mentioned by a lot of authors of a lot of papers. Partially specific data are too abstract. We don't have enough details to work with. We oftentimes see that when a code line is formed with multiple elements, then you get the return value any string, and it's not usable. It's not very helpful. None of the analyzers would analyze that code. They would go from the entry point, and if they don't go into the dead point, they're not going to analyze it. So, do you think you can use the existing analyzers? Well, yes, you could, but it's not a trivial issue. Hence, we decided to write our own analyzer. One of the main ideas was that it has to be light, so as to work at JavaScript-coded client-side web pages without eating up all the memory, right? So this is the paramount requirement. Our is rather naive. It doesn't use fixed point solver. If you know anything about static analysis, you know what I mean. It only has two abstract meanings, unknown and framework. Right, so on to the analysis algorithm. Here it is, on one slide. Let's zoom in. And no, you don't have to read it. So I'm going to comment on it. So analyzers look for the function invoke instances, and we want to determine the arguments of the function. If we understand the arguments of the function, we're going to understand the request sent by the function. We look for embedded fetch and XML HTTP requests, and also we're looking for requests to popular libraries like jQuery, etc. We're not going to analyze inside. We're going to look at the requests sent towards those libraries, and we're going to use signatures to do that. They are going to be syntactic signatures that only include names. We just use the abstract syntax tree, the AST, to do that. We know that Axios is called Axios, and Angular is called $HP. So, how our algorithm works? It works on AST trees, we don't use CFG at all. As the tree is traversed into depth, and we remember all the variables and the values. Breve analyzer is incapable to identify the variable. It has a specific value called unknown. When you encounter a special request like Ajax or etc., the analyzer tries to calculate it and calculate the arguments of that function. In terms of data, the way we model data, the analyzer supports a specific data, primitive types, numbers, null, ABC, etc., and everything that any system would have, like GS, and also unknown and from arg. Unknown and from arg mean that this is something that we don't know, and from arg means that it comes from formal arguments of functions. When we look at that function, we don't know the values inside the arguments. You can only tell when it's invoked. So for unknown values of function arguments, from arg is used. And then the analyzer is incapable of understanding that variable can take several values. If it were to remember one value, it would have to get rid of the other value. It goes all the way to lexical scoping in its identification. The analyzer would differentiate between various variables. Like we have global x as local function of f, and one x in block. So the analyzer would differentiate between these three types of access. This can be done using Babel library and other libraries, rather than just parsing and getting the AST. You can also parse it in a different way, more precise way. You also have a whole set of embedded operations. Not just the variables, not just the arguments of functions, but also the operations like plus, etc. As far as requesting user functions, we ignore it. If it's there in the code, we don't even dive into the algorithm wouldn't even dive into it, would just assign unknown to it. Branching. All branches are only crawled once. If you have a cycle, we only enter this branch once. If you have an if, then we get into evals once. And the factual analysis consists in us searching through the AST. So here we have a code in 7th line we have $Ajax. So we go from the very top, and we can see API-based URL, which is calculated using the data that we know. We know location. We know all the data on the web page. The second component is literal, so we can calculate it. Class is supported, I already mentioned that. Then we go into the body of the function. This function has 3 arguments. We don't know the values of those arguments. We don't see requests from this function. They might be non-existent. So we assign from arg, right? Then if. We don't do anything with the if. We ignore the ifs. We don't go inside the branches. Then cache get analyzer doesn't know anything about it, so the analyzer just ignores it, and then comes all the way to else. Speaking of ignoring, should we have a dast, it would have go into else. It would have go into the right branch and not fall into exception, so that this request happens. In SAST, you don't have to have it. You can ignore anything that bothers it and just go into the line of the code that it needs. So we have the URL field, it can be calculated, all the data that we need are there, and we remember the values, and we can put them together. So the arguments of this request is known. The URL, the date, record limit and format, all the three fields are there. The record is from arg. We don't know what is there, right? But it's okay. So we have s.ajax call, and we have the URL, what it is calling. So the analyzer, in its hardcore, in its functions, already has it all. What we have highlighted in blue are the data that come from the arguments, function arguments. Record is now unknown. Both unknown values are now unknown. And the rest are transformed into arguments the way it works in $Ajax. So this was what was the basics of the algorithm. There's also this mechanism that we call looking for argument values. Let's say we have a code, and rather than a function having local variables, known variables, and calls the server, but it comes from arguments, function arguments. If our call depends on function arguments, we need to go deeper into it. How is it going to work? We are using from arg. I mentioned it already. If from arg encounters a $Ajax or something, then it means that this call depended on arguments, and we need to look for these calls and the types of arguments. How it's done in practice? We have call f. We need to find the calls. How are we going to do it? Again, this is another very difficult task for JavaScript and other languages. We need to build a graph of calls. We had a variable table. We're going to search for the variable table. We're going to search for the variables that indicate that point towards f. And it's going to only work for variables, not for the function arguments, but it would work for variables. So this is how it works. So we have function f, where all the way to as $Ajax and from arg is there, so it means that we want to understand the arguments, and we want to identify the calls. Function f creates a variable in the scope, and this is the variable that is called back. And that's why it's not difficult for the analyzer to find J and K. Okay, what's next? Analysis is going to go from J and from K, and the moment we arrive to the call of interest, we're going to enter it. We're going to repeat our analysis from J and from K, and we're going to kind of model the function call. At that, we've been to f, right? We've analyzed it. But now we're going to have arguments calculated because we've been to the place where it's called from. G calls for f. We know that. Now we start from J. And we see variable options. And we can see that the argument is sent there. And we go to the beginning of f. Now we have a different situation because some parameters are already known, and when next call as the $Ajax happens, we already have certain arguments. So that way we found one of endpoints. Then there is this read variable. It goes to f. And then we go once again to f, and we get another set of arguments. Sometimes there is a chain of several calls. Function f is called from G, and G is called from K. How do you detect that? Well, you analyzed J and f chain, and you get to $Ajax or fetch. If by analyzing two-element chain, you see that from arg is still to the f has gone to the f function, it means that we want to analyze a longer chain. It means that f sent its arguments, or rather would take it from somewhere and would send it over somewhere else. So first we calculate f from arc, then when we enter f, it again reads from arc. So the analyzer understands, okay, so now we need to search for G to find more precise arguments. So how this is done? We have a lineup, and if you are all the way to $jacks of fetch and you see from arc, you add just one element on top. So you just takes one first line, like G in this case, and puts it in the beginning of the line. So now we start from K, because we realize that K calls G, and then we go to G, and we can calculate it and go all the way to $jacks. So much for the algorithm, a very high-level review of our algorithm. And obviously, it comes with certain difficulties. It's rather simplistic, so it is not universal. A static analysis, JavaScript static analysis algorithm is a difficult thing. JavaScript is difficult to be analyzed statically, and so here are the difficulties that we have. Dynamic download of eval code is one such problem. Bundles and object-oriented programming. If you have this, you need to understand where this points to. We need to also model the DOM, and it's a difficult thing to do. This .make request is not something that our analyzer would find, or a equal require jQuery a .get. So you find everything that's related to signatures, but a will not be interpreted as jQuery. So one way out is to complicate static analysis, but it's still difficult for static analysis to analyze JavaScript code. So one other solution would be to go hybrid, to combine the static and the dynamic analysis. I mentioned already that purely Dast is not something that is good for us because it cannot analyze that code, but at least it can hint to the static analysis. So we can take a real browser and download the page in real. So if some code works in it, we can get it using debugger, and since it's a real browser, irrespective of whether it's been eval or deciphered going from server, it's there in the real browser, and this way we can find the whole code. Besides, we get all the calls that you would regularly get when you download the page. The analyzer would have it, and we also have access to DOM tree and DOM AP. So if a value is taken from DOM, we no longer have a problem to understand it. We have access to the trees. We have the exact model of the browser, So the idea has already been realized in our analyzer. The first bullet has already been done in the very basic version of the algorithm. There are a couple of other ideas that we're going to experiment with. Picking into dynamic. We want to know the value, but it's difficult to analyze statically in JavaScript. What can be done? We can analyze this code dynamically. If it has been executed, then in debugger, we could check what was the value in dynamic at that point of time. We would be able to look at all the values. So in dynamic, we at least can get some of the values. It can work for data, for base URL or anything, or for functions, where the function points at, where to get the data. Another point, say function calls $jacks that sends a request to the server endpoint. Analyzer fails to do it. We can try to invoke this function on the page and probably would be lucky enough for it to send a real request and we'll catch it. Or probably we're not going to trigger that, but at least we'll get some data. The function would require a module and we'll see the real meaning of this particular module, and this would prompt us in our analysis. Okay, this was all a bit abstract and theoretical, how it works with real vulnerabilities. What kind of vulnerabilities can be identified in JS in reality, and what our algorithm can work for? So we experimented. Generally speaking, the experiments were built in this way. We would take real web pages, we would get endpoints, and then we would scan it with web scanner. So first thing we found, a couple of vulnerabilities in Severe. One of them is has been already fixed. It was an SQL injection in WP discos. And also another one, and we also identified 10 day. We actually reported it yesterday. In bug bounty, we also identified a PHP insecurity, SQL injection, and a couple of cross-site scripts, XSS. So, two CVAs. The analyzer finds the endpoints, and it's not something that can be just caught by dynamic crawling. More multi-step crawling probably could have found it. And from as far as bug bounty is concerned, we have one SQLI and 6 reflected XSS. Most of them can be found by the analyzer, but not by the dynamic crawler. So for the bug bounty endpoints, we used one-step crawler. He tries to just go through all the interactive elements, single-step ones. So three of the endpoints were not found with this type of crawling. And now on to the code. This is from bug bounty. The code is changed. Well, first off, for you to not to find the website, and it's also a bit simplified. You can see here $Ajax, and it's called from the thing that's regged in that option. So where we analyze it, we didn't have that element. There was no search car ID thing, so you couldn't find it with dynamic crawler. Probably in some other place in the site, it's there, and you can find it, but not in the pages that we looked at. We couldn't trigger that request at all. A second example. This longish line of code there is if, and also a $post. I know it's very difficult to see, so I'm going to show you like that. So please pay attention at what we have in if. In this if, we have 20 variables, and this 20 variables calls 20 arguments and 11 validation conditions. And all of them have to be true for this element to be executed. So basically it means that unless we enter the if, unless we turn all of them to true, unless we fill in all these forms, nothing is going to happen. What's your dynamic crawler is going to tell you? Hard time, huh? And just a very brief example, not too unique. A WordPress plugin the CVE thing. So two functions here. The second one is called from the first one. GetObjects obj is called from the previous function. So it downloads additional comments onto the page. The analyzer that analyzes chains would find it and look for all the elements in the chain. And in dynamic crawling, it's a problem. You have some comments that is not there on the page, and you'll have to download more. But if you don't have too many comments, you wouldn't be able to call it. And this is an issue for dynamics. So what the analyzer is going to find, if the code is done in jQuery style, if the code is simplistic, and it often happens in WordPress plugins, and in complicated websites as well, when the code is difficult a lot on the client, but request is simplistic. Just fetch, and it's pretty easy to calculate the arguments. And these could be triggered with various complicated actions, but it's okay for the analyzer. Sometimes you can't really call it on the web page. We call it hidden functions, but in fact it's that code. So when it happens, when it has to do with an authorized zone, a lot of excess code is bundled on the page, and sometimes this bit of code has to do with the admin. Because we haven't hacked it yet, right? But probably there is authorization vulnerability, and if we find those endpoints, then we'll be able to do something about it. In rendering Markdown Jira, you also go through that endpoint, and you could leak, take away user emails. If you don't have login, you don't see it in the login, you see it in JavaScript. Or a function that somebody forgot to delete. In some other cases, crawling works better. Say, request is set in a difficult way, and it can easily be triggered by just pushing one button. And here are some difficulties enumerated. Right, and now the demo. I'm not having a internet. Please use this link on your own. You're going to use it and look at the demo and play with our analyzer experiment. So hopefully it keeps working all through the conference. I'll make it work. To conclude, static analysis can be more accurate when you combine it with dynamic analysis, and a lot of articles mention it as well. Another point, I mentioned that our algorithm is not validated, it's not super scientifically correct. But our vision is this. If you don't have an existing solution, you'd rather do something simple that does work and then complicate it later. As far as endpoints and vulnerabilities are concerned, none of the methods is a silver bullet. The GS analysis is not better than dynamic crawling. It's rather a complement to. Dynamic crawling is better in some things, in some data entry points, and static scanner is better in other things. Static scanner is good at searching endpoints. We were surprised not to find any existent solution, out-of-the-box solution to mine endpoints. While scanners, out-of-the-box scanners, do have analysis of JavaScript code. In WebScript scanner, it would look for DOM and stuff, but not the endpoints. In fact, you basically want to use both the scanner, the static scanner, and the crawling. With this, I would end my talk. And I'd like to use this opportunity to thank the audience. And this is the link that you had earlier. And please play CTF with us. I'm here representing Bushmakers. And I can see you have some questions. Please use the mic. Thank you, Danila. This was really cool and interesting. My question is this. How about open sourcing your solution and use integration of your search engine, endpoint search engine, into the existing dynamic analysis, like a plugin, a probe suite or something, or a browser extension for that matter? Thank you. Brilliant question. Well, first off, indeed, I want to make it into open source. I want to do it, but not yet. I haven't done it yet, but it's my plan. As far as integration is concerned, we experiment integration with the one you mentioned, but not the plugin. We had the idea of a plugin, but we haven't realized it yet. We already use a managed browser for dynamic analysis for that, but it's not exactly your plugin. Say you want, what I mean is it's something like community collecting the endpoints rather than, Yes, yeah, I totally agree with that. And as soon as I have it open sourced, it would be great. Thank you. Thank you. I can see a question from there. Yeah, I already have a mic. Where are you? Yeah, I'm here. Thank you. Brilliant presentation. I was trying to solve a similar issue, so I'm going to have several questions on things that were difficult for me. So my question number one: what is the capacity, number of websites per minute? Great question, thank you. Usually it would take from 20-25 seconds all the way to several minutes. Some websites would force the analyzer to go into loop, but we managed to do it in such a way that it would work for not more than 1 minute or minute and a half per site. One stage, we really want the page to be downloaded. There's a timeout. By default, it's 3 minutes, but usually the web pages download faster. Right. I'm going to pronounce a swear word, WebSocket. How you handle WebSocket? What you do about it? How you go about them? We don't support them. It's actually a very interesting idea, but it's not within our scope at this point. It's just that WebSockets can also be data mined all the way to doing a DOS attack. Absolutely, you're absolutely right. And it's an interesting task, but it's not something that we're dealing with right now. I'm not here calling to DOS WebSockets. Yeah, I know. And another kind of scary word are WebAssemble websites. No, not yet. We don't do anything about it. Look, how about giving an opportunity to, because you seem to have a lot of questions. If you don't mind, let's take it to the margins of the events. If you're interested, you actually do approach me. I'm an open guy. I can answer all your questions. Thank you. Yes, I can see a hand over there. Thank you. Very interesting presentation. It might sound silly, but my question is this. I'm interested to know the logic of you working with redirect. Do you look at it as a separate instance? And okay, so when you download a web page, if analyzer wants to analyze a web page, it opens. If it redirects, then it would go through the web pages. And as far as endpoints are concerned, we mine the initial request. In static analysis, we don't really know whether or not redirect is going to happen. Actually, whether or not it's best to be in styles or not. I mean, when we do analysis, we don't know anything about React whatsoever, and we'll look just at the initial one. But redirect can be part of endpoints. Don't you agree? Good one. Yeah, to share. Speaking of endpoint definition, good, interesting. And a follow-up, JSPC. gRPC. Can you do gRPC from browser? Yes, you can do it now. And it would be similar to WebSocket communication, same level. You know, just as a follow-up. So gRPC works on top of HPC? Right, and we don't know anything about it. Yeah, okay, for later. Right. Out of mic. A comment out of mic. Is it gRPC or? Okay, anyway. We haven't looked at it yet. Can't tell you anything. Right. Okay, it's time for you to pick the best question. Oh, tough choice. This guy, the guy in the green shirt. Great, thank you. Thank you very much.